here's a good template for using a tokenizer. So you can go from transformers, import the tokenizer that you want. There's loads of different tokenizers available. This is the one that's used for that model BERT, which creates representations of text that we'll look at in a second. And you can get that from the pre-trained weights just by specifying the model name. You can follow this pattern for loads of different tokenizers in Hugging Face, but this will give you a tokenizer which can be called on some text to encode that text into different tokens. And then take a look at the Hugging Face documentation, see if you can do some of these steps. So I've got this BERT tokenizer, dot encode. So where would I find that in Hugging Face docs? Let's do tokenizer pre-trained. See if we can find that. These docs are not great, I don't think, or at least I'm not used to using them as well as I should be. But let's see if we can find that in here. Pre-trained tokenizer. What's this encode method here? This is the one that you want to use. So you can see this encode thing here is a method of the pre-trained tokenizer above. And what that means you can do is you can use all of these methods below. And the one here is, pre-trained tokenizer encode. So if I do encode the sentence, and then let's say I print that, tokens is equal to this, and then print the tokens, and run that. We need to run the cell above. This cell actually downloads the model as well, and you can see all of this happening here. Back here, print the tokens. So there are the tokens. Those are the different unique IDs, essentially, of the different tokens that I've got in that input sentence. Hello world and welcome. That is a 4-word sentence. This clearly has 6 different tokens in. So what's the difference there? Why is one longer than the other? If we were to decode that tokens, I think we can just do this as such. But tokenizer dot decode tokens and then print that. But tokenizer is not defined. Then you can see you've got this CLS and SEP on the end. Roughly, CLS represents the start of sequence token, sometimes the SOS token, and the SEP represents the end of sequence token, or EOS, in some data sets. But the way that BERT's trained, it has these different named tokens, but the way you can think about it is they just represent the start of the sequence and the end of the sequence there. And that's why this 4-word sentence comes out as 6 different tokens. So the decoding of any tokens will not only convert those token IDs back into their text representation, but also combine them all together into a string. So in the tokenizer, the BERT tokenizer has a bunch of different useful methods, including convert IDs to tokens, convert tokens to IDs, which I believe works in that way. So let's take a look at that. So there's the list of the separate individual words. So the decode is basically doing that and then combining them. Essentially this. Almost, roughly. It's joining them together. Tokenizer can do a bunch of other stuff too. So the vocab is the assignment of this integer index to each token. For each token to have a unique representation, we need to begin to make it more mathematical. The first step there is to represent it by an index. So each token has a particular index. And that mapping between the word and the corresponding index, we call that a vocab. You can see when I do BERT tokenizer dot to get its methods and attributes, there is a get vocab method. Where is it? There it is. And if I print that, you'll see that you get this dictionary between all of the different tokens, which BERT has a representation for, and a unique index. In this dictionary, you can see there's a lot of unused tokens. Those ones are basically spare spaces left in BERT's memory that you can use to either add your own tokens or do something else with. But beyond those, you get at the beginning some special tokens. Well, all special tokens, you can tell them because they're enclosed in square brackets. You get things like the padding token, which is used for making sentences the same length when you process them. If you scroll all the way down past these unused tokens, we'll get to the real words. And it's too long. It's too long to print there. BERT has about 30,000 word representations in its memory. And what we're going to do is get to looking at what are the vector representations for each of those word representations. And hopefully, if the visualization works well enough in Colab, because it's sometimes temperamental, we'll be able to see the 3D plot of how different words are represented by BERT, hopefully in a way that similar words appear in similar places. So let's move on to that then. So we've looked at so far that we've seen the corpus, the tokens, the tokenizer, and the vocab. And those are essential things to understand for all of the pre-processing that goes into natural language processing. And then beyond that, we've seen that we can represent words as indices. So we take a word and we give it a number, which basically represents, which number word is this in my set of all my unique tokens. And that's the index. An alternative way to represent that is like this, as a one-hot vector. So you might hear about this or see them in some places. One-hot vector is 0 everywhere except 1 in the position corresponding to the index of the item that it represents. So this represents word number 2. 0s everywhere except for the 2. This is a way that we can begin to make the words a little bit more mathematical. It's not particularly more useful than an index, other than the fact that it shows that words are not on a single scale. Word number 1 is not smaller than word number 100 because they're just not on that same number line. So this is a little bit more useful of a representation for the words. It shows that all of the words are different. They don't line up on the same axes. But if we represent all different words like this with a one-hot vector, what's the problem with that? For every word, we need to add another item to this vector to store the representation for each word. If I've got 30,000 words, or something like 130 in the English language, then I'm going to have that long of a vector. So with increasing words, I need to increase the dimensionality of each vector that represents that word. That's one reason. The specific case of pluralized words or the same word, maybe in a different tense or something like that, those things are represented as totally different words. There's no similarity at all. If you do an element-wise comparison between the two words, then there's as much match between those very similar words in practice and totally different words. But the generalization of that is that basically every word, every different word, every different token that you want a unique representation for, they are all totally as dissimilar as one another from any other word in the dataset. Very similar words are not represented by very similar representations. And it makes sense that they should be. If I have two words that I want to kind of produce the same sorts of responses from a model, or two sentences which say the same thing in a different way, I probably want to represent them in a similar way. So we want to move on from one-hot vectors and address those problems. And the approach to that is to move away from this visualization of one-hot word embeddings, where each different word is represented on a totally different axis, and the dimensionality of your space is as big as how many words you have here. I've got 3 words in my corpus here. That's a 3-dimensional space. I want to move away from that to provide a more rich representation of the word, where the words, which have similar meanings, have similar representations. And that, to Dali's question earlier, is what a word embedding is. So a word embedding might look something much more like this. In this case, I've got 4 different words represented in a 3D space. That is, each word is represented by 3 numbers, and those 3 numbers are not just 1s and 0s, but they can be any real value, such that similar words should appear with similar representations. And that is what a word embedding is. So comparing one-hot word embeddings to these new dense word embeddings, you can see that we've got the one hot word embedding on the left, and a dense embedding, typically this is what we refer to when we say a word embedding, might be something like this. It's full of values, and each of them, like the activations in a neural network layer, hopefully they represent something high level, meaningful, and abstract about the word. They represent the information of the word compressed into this vector representation. And typically we have maybe 300 dimensional word embeddings or 128 dimensional word embeddings. The bigger the word embedding, the more information you can represent about the word in that embedding. So what I'm talking about here is that each of these vectors represents one word. And so hopefully they represent some high level concept, right? So maybe that 16 is like how positive is this word, and that -2 is like how, related to retail is this word, or something like that. They represent something high level, which should contain the meaning really of the word, rather than this just kind of, this just purely very mathematical representation of the word on the left. So those word embeddings, they are the final representation that we want to have of each word. For every single word which we hope to understand, you need to have a word embedding. The question is, how do you create those word embeddings? There are a few ways there's a bunch of ways to do it. There are a few algorithms which are specifically designed to create word embeddings, like word2vec, and that's kind of the original word embedding algorithm. It works as such at a very high level. Initialize random embeddings, take pairs of words that appear close together, calculate their similarity using their random initial embeddings, and then maximize the similarity between two words using gradient descent. So it's basically you have like a one hidden layer neural network. It's equivalent to that. You're passing in the representation of one word. You want it to predict this neighboring word is likely to appear nearby with high probability. What we're going to look at is how they can be learned by other models and pulled straight off the shelf. And BERT is an example of a model which has learned a representation for a specific problem. So in PyTorch, you may find this embedding layer. The embedding layer is the kind of thing that you might see in a lot of models, and it contains all the parameters which represent the different word embeddings which this model can understand. So you might have, if you've got 100,000 words, each with 128 dimensional vector word embedding, then this layer would have that many parameters. This layer is essentially, as it says, a simple lookup table that stores the embeddings of a fixed dictionary and size. So basically every row is a different word, each column is a different element of that word of that word's representation. And if we jump back to what I want to do here is basically show, let's take a look at BERT and get the embeddings from inside it. So if we run the cell above, up here, this runs and this gets the BERT model. Just gets it from pre-trained in Hugging Face. And down here, you can run this and print the model modules. BERT's a pretty huge model, so you can see it's got a lot of different layers in. And the first one you can see is that embeddings layer. So this is where we should find, or this specifically, is where we'll find what representations this pre-trained BERT has of the different words that we've got. Now, the pre-trained BERT has pretty good representations of words, so we should find that similar words have similar vector representations. And what I want to do is take these words out and try and visualize them using TensorBoard. What I've got here in the next cell is basically just the number of embeddings that I want to get out of my model. I don't want to use all of them because because it takes long later. But then I've got this line, model.embeddings.wordembeddings.weight.detach. What does that do? Where did I get this from? Well, in the cell above, I printed all of the modules, and in the top, you can see I've got this embeddings. So these are the different layers of BERT. The first one is this named layer, it's called embeddings. The next one is this thing called encoder. So if I get .embeddings, it's going to give you all of this. And all of this is just one big torch transform. And it has these attributes inside. It has the word embeddings attribute, it has the positions embedding attribute, it has the token type embeddings, etc. This is the one that contains all the parameters which represent the representation of each of my different tokens that BERT understands. So I've got 30,000 of them by 768. So to get those parameters out, if I want to actually get them, because I'm going to try and plot them later, I would do this. And that gives me a PyTorch layer. Then I want the weight from that. We saw that, I think, in one of the first lectures was, you can look at the different parameters, .weight, .bias, and you'll get the values in there. And then I had this funny thing on the end, .detach. I want to prevent me changing this thing from affecting the model, because these are like model parameters, which I've got here. If I didn't do .detach, I'm like playing around with the model parameters. So if I like add 1 or something, it's gonna skew the whole model. Or if I maybe compute something from this value and then do .backward, it's gonna update not only the parameters which I was doing something with, but also the parameters of BERT earlier in the model. So you want to do .detach to create a new instance of these parameters and store them in a new variable. So here's my embedding matrix, print embedding matrix .shape. Run that. That's my shape. This represents how many words I've got the embeddings for. This represents the embedding. And then this is where we played around with the vocab. I looked at the vocab. You can see everything in there. So once we got this vocab, which is a dictionary, I can index it with different words. And I should be able to see the ID for that word. Where is it? There it is. So the word hello has ID 7592, and you can do that for any other words you want. If I give it some broken word, it's still going to give me an ID. No, it's not, sorry. If that's because it doesn't recognize it. Instead, this word will be represented by unknown. That token unknown is token number 100. So during the tokenization, when I turn my strings into the unique IDs, I'm going to replace anything that's unknown word or unknown token with this. So knowing that, we can map between the different IDs and words to understand in this embedding matrix, row 500, what word does that represent? Row 600, what word does that represent? But I can't go from ID to token here. I can only go from token to ID. That's how getVocab works. I think there's another method for this. What is it there? There's so there's convert tokens to IDs, convert IDs to tokens. I could use either of those, or I could just reverse this dictionary. So later we'll use that. Down here, I've got a function. I've got a function which should, if the visualization works in TensorBoard correctly, it should take my embeddings. It should then call this function, which is going to create labels for the embeddings. This is a bit fiddly, don't worry about it, but it'll basically allow us to highlight words by their length or by the number of vowels or by whether they're a number, so that we can compare whether those groups appear similarly or not. And then down here, we've got this visualize embedding function. All it does is it uses TensorBoard summary writer, add embeddings method. And this one takes in the embeddings and their labels and the label names. So let's see if we can get this to work. It's going to run, it's going to perform the embedding, or well, it's going to take the embeddings out of the model, it's going to put them in TensorBoard and should show them when we run the next cell. Cool, embedding done. Let's run this cell here. It's 30,000 tensors, each of them has 768 dimensions, so it's pretty big. The only thing you need to be careful of is that this is correct. So, here, and this might make a good social post if you want to take a picture of it. Here is a visualization of all of the different words represented by BERT in 3D space. It's been projected down into that 3D space. And there's a lot going on there. Just so you can see how this works, here's the name of the label, and here's how you calculate that label. And then in TensorBoard, you can change this so you can see, or you can color them as such, right? So here is everything colored by the number of vowels, or it's colored by whether it's a number or not. So there you can see there's all the numbers. This is a principal component analysis of the 768 dimensional vectors. So you've got these 768 dimensional vectors, and you basically want to say, which directions do they vary most in? And the top 3 directions, take those as the X, Y, and Z coordinates. I just wanted to point out something for those of you who are wondering what's happening here, because there's a lot of numbers being thrown around. 768, you got this 3D space, you got 30,000, and there's something about PCA, so I wanted to bring all of that together. So what we're looking at here is a 3D projection of very high dimensional, 768 dimensional vectors. So of course you can't visualize something that's 768 dimensional. The way you should think about it is just, okay, it's like 3D, but with more axes, okay? It's like an arrow in this space, much like an arrow in 3D space, except there's many more dimensions. And so PCA is a technique, a dimensionality reduction technique, that's been used here to project the most useful components into 3D space so that you can visualize it. How does it work? It works like this. I'll try and do a little illustration. Let's say you've got this 2D axis, looks like this. And in this 2D axis, you've got some data which looks like this. The data is all along that line, okay? The data is all along that line. And the thing with that is that, well, I've got 2D data. Each of it has an X coordinate and a Y coordinate, but there's actually not much use in having both those coordinates because they're totally dependent on each other. And what would make sense is that I say, okay, well, really, I should just use this as the X coordinate, and I should take these axes and basically rotate them like that so that I can represent all of my data along one line, and I can just give the X coordinate, because they all have the same Y coordinate. That's what PCA is doing, roughly. It's just resetting the coordinates in the direction which the data most varies. And once you've done that, you can throw away the higher dimensions. So like here, I could throw away the y-axis because there's not much information included in that direction at all. In fact, it doesn't vary at all. So this direction here, we call this the principal component. That is the direction the data varies mostly in. And you could do that in much higher dimensions as well. Now, sometimes you'll have not all the data sitting on just a line, but the data sitting maybe around a line. So you might have data not just on that line, but kind of around that line. So in this pure case, the green line has actually no variance in this direction at all. But you might have some data which hovers around that. Now, that means you can't just throw away the other axis. You are going to lose some information. But if you do that in decreasing order of which direction they vary most in, you should only be left with the most important components, the three most important components if you project into 3D. And that's what we're looking at over here. What happens when you do PCA is you take all the data, you calculate its covariance. That is a set of axes which point orthogonally from each other, and they tell you in each of those directions how much does the data vary. And then you just remove them in increasing order. So remove the direction where the data varies least, and then second least, then third least, until you're left with these principal components. And that's what these three are here. Note, a lot of information is lost. Like almost all of it is lost by doing that. You can see that down here when you look at the three different components. You can see, okay, here's the 10 top principal components. The first one captures 6.6% of the variance. The 10th one captures 1%. And total, in 3 dimensions, we've captured 12.12% of the variance. So 87.8% of the variance is you can't see that here. It's been thrown away because we've had to sacrifice things in order to be able to visualize them. So this is the 3D production of that space. What's TSNE? TSNE is just another dimensionality reduction technique, one where I believe it is points in the original space remain close in the projected space. But it does it iteratively. So if you really want to burn out my laptop, you can click this, and it will try and visualize the PCA algorithm progressing, which is not just a one-off calculation, it does it iteratively. So initializing TSNE. Now's where I could really do with the GPU, but all of that is moving. And it's going to try and cluster together similar parts, I believe. What's going on here? We can zoom in on it, we can select it, we can create the function to define how to label it. Well, if you print out the vocab, it contains a lot of words which are covered by square brackets, indicating they're special tokens. They're called unused. They're not words which are unknown. Unknown words are represented by the UNK token with square brackets either side. The unused words, I believe what they're for is for when you fine-tune BERT on your own dataset, you may have words which come up in your context much more than they do in general. So they might not exist in the 30,522 embeddings that BERT has learned. So you could fill in those embedding layers, those unused token representations with something that makes sense in your case. Essentially, you can add to the existing set of representations which BERT has using those fillers. All right, so I mean, there's something quite obvious happening over here, right? If I color them by length, all of these are 3 long. And if I label by the word, you can see these are all the unused tokens. What is this actually? Oh, this is the, sorry, I'm coloring by the number of vowels. So down here, you can see these are all the unused tokens. They have very similar representation. They don't represent much, really. What about all these pink ones over here? They're all numbers. All numbers over there. These blue ones, not sure. It's like more numbers. Yeah, they're just 4-digit numbers, aren't they? We can look at is number. So you can see here, all these red ones, they're all numbers. The others are all words. This is really where the interesting stuff is. Okay, well, I mean, if you click on any word as well, the next thing I want to show is it shows you the words most similar to that in the original space. You can see they don't look very similar in this projected space, but if I click aristocracy, the next word that shows up is nobility, aristocratic, elite, etc. You can do that for any word, and you can see which are the closest. So essentially, this is a nice little similarity search tool built into TensorBoard, which can be nice for understanding, hey, are your embeddings reasonably accurate? And yeah, and then kind of where does different stuff show up? So I want to introduce one final challenge. These word embeddings can capture analogies in words. So if you have a word analogy, which is something like A is to B as X is to Y, then you can kind of compare like, right, well, what's the difference between A and B and how is that applied to different words? So for example, London is to UK as Moscow is to what? Cat is to kitten as dog is to what? Does this kind of vector math work out in embedding space? And this notebook's an illustration of the fact that it does. The way that works is we take BERT, we get the pre-trained model, we get the BERT tokenizer. Take a look at that in Coda there. Print out the modules again. Get the embedding matrix. Not found transformers. You know what to do there. Just pip install transformers. Run that. Install transformers. Run the next cell. All the way to down here. This is the visualize embeddings function that we used in the other notebook. And then here is a function which gets the word embedding given a current word. It basically indexes the embedding matrix for a particular row. That's the embedding for that word. And so it gets that word embedding. Well, what we want to do is be able to look up the nearest tokens to an embedding. So if we got a word, we use that function just defined to get the embedding. And then we go through all the other words, look at what their vector embeddings are, and compare those two vectors. You can do a cosine similarity to compare them for similarity, and that'll be a measure of how similar are these words. This function basically goes through each of them and gets the most similar n words. And this function here, just down below, is the analogy solver. So I don't have torch metrics either. So let me just install that. Pip install torch metrics. Run that function to get the word embedding. There's all my, well, there's one of my word embeddings, just one, massive. Get the nearest word embeddings. What am I printing there? I'm just showing the similarity indices, which I've calculated there. And this function is where the bulk of things happen. So this is the function which solves the analogy. It says A is to B is what C is to D, given A, B, and C, and returns D. So essentially it takes an A, B, and C, gets the word embedding for A and B, cat is to kittens, calculates the difference between those two representations, and then it's going to add that to the third word, C. So it's going to add that transformation vector on and comes up with a final embedding. Then the challenge is, what's the nearest word to that embedding? And so we basically iterate through the data set, find the nearest embeddings, and print out the top n tokens. So if I run that, define that function, down here you can see some examples. So I solve the analogy. Man is to woman, as king is to queen, is the top pick. And then you can see the top 5 related after that. London is to UK, as Moscow is to, UK comes out first. Puppy is to dog, as kitten is to dog, dogs, cat, right? So you can see it might take a few. It's not perfect, And funnily enough, in a lot of cases, the closest word is actually the original word, which is why it's got this this skip line over here as well. With looking at this and coming up with different functions to explore that. But you can see similar words should appear similarly. And this Analogies notebook is an application of using that visualization.